Hi folks, this is the third problem in the optimization lesson. So here they're asking us to find the point or points on the parabola given by y equals 6 minus x squared that are closest to the point 0, 3. Okay, now the first thing I notice is that the point 0, 3 is not on the parabola. I guess in that case there the distance would just be 0 because it's actually on the parabola. So let's draw a picture to see if we can figure out what's going on here. Okay, so I'm going to start by drawing the parabola 6 minus x squared. So negative x squared will just look like that, and I'm bringing it up by 6 units. So it'll be a parabola that looks like this, and it is symmetrical about the x-axis. Okay, this is going to be 6, and the x-intercepts would happen if I were to solve this. X squared equals 6, so x equals negative root 6 and positive root 6. All right, and the point that we're working with is 0, 3, so right in between 0, 0 and 0, 6. Okay, and we want to determine the point or points that are closest to the point 0, 3. Okay, so when we talk about being closest, we should be thinking about using the distance formula because we're going to be finding the distance between this point and some given point or points on the parabola. Now, what I'm going to do is I'm going to draw myself sort of an exemplar of where this point might be, but just to not throw yourself off, try not to assume that these points are going to lie in some special place. Like I'm not going to draw my point so that it's completely horizontal to 0, 3. I might start to think that that's where it's going to be. I can't assume that this is going to be the closest point. So I'm going to choose something that's maybe generic. Okay, and you know, if I have a point like that, because of the symmetry about the y-axis, it might not be surprising if I do end up finding a second point. Okay, but I'll use this, and since it's a point I don't know, I'll just call it xy as representing a point on the parabola that's closest to 0, 3. Okay, now before I start to write any equations, you know, this point, while it's unknown, doesn't lie just anywhere on the Cartesian plane. It lies on this parabola. So that means that the y value is actually just given by 6 minus x squared. So even before starting, I can start to reduce the number of variables that I have to work with. Okay, so essentially what I have to do is come up with a formula that measures the distance between the point x, 6 minus x squared, and the point 0, 3, and minimize that function. All right, but we have an equation that gives us that, and that's our distance formula. So let's recall that the distance formula, I'll use capital D just so that there's no mistake with the D we use in the derivative. Okay, and we know that that's the square root of the difference in the two x values, so x2 minus x1, okay, squared plus the difference, the square of the difference of the y values, y2 minus y1 squared. And essentially, this is just an application of the Pythagoras theorem. All right, so let's now start inputting what we have. Well, we have our x value minus the x value here is 0. So I'm just going to have x minus 0 squared here. And then plus, well, y2, 6 minus x squared is my y value for this point. Okay, minus the y value on 0, 3, which of course is just 3. Okay, so let's clean this up and then see where we're going to go from here. So here we're left with just x squared, and 6 minus 3 is 3, so I'm going to have plus 3 minus x squared all squared. And I don't think I'm actually going to expand this, because in the end, it's going to be pretty ugly. I'm going to have to use, I'm going to have to take the derivative anyways, and I'd rather just use the chain rule instead of multiplying this out and ending up with like an x to the 4th in there. Okay, so I'll choose to leave it like this. So here now is we have a function for the distance between the 2 points given in terms of one variable. So notice here we did do a substitution. We just did it earlier on. We realized that the y value can be written as 6 minus x squared. Okay, now let's determine what the domain of this function is. Well, technically, the domain could be all real numbers because this point could lie anywhere on the parabola. But it's very clear that it certainly cannot lie anywhere beyond negative root 6 and positive root 6. And let's just do a quick justification here. The distance between these 2 points is 3. The distance between this point and 0, 0 is also 3. So if you think of drawing a triangle here, this distance already is going to be more than the distance to 0, 6. Okay, so there's no way that the shortest distance will lie on some point below that. So what I'm going to do here is, just to make things easy, is I'm going to restrict my domain from negative root 6 to positive root 6. Okay, because I know for sure it can't lie anywhere beyond that based on my justification. And what this does is it gives me a closed interval in which to work with. All right, so now we have our model, we have our domain. Let's go and apply the calculus here. Okay, so my derivative here, and while I'm using the prime notation, it's implied that the derivative is with respect to x. Okay, so again, think of this whole thing as something to the 1/2. So that's just 1/2 times x squared plus 3 minus x squared squared to the negative 1/2 times the derivative of this inside function. Okay, so that's just 2x. And then here I'm going to apply the chain rule. So u squared is going to be 2u. So 2 times 3 minus x squared times the derivative of 3 minus x squared, which is just going to be negative 2x, because the derivative of 3, of course, is 0. All right? And just to make my life easier, hey, this whole thing is going to go into the denominator. Now we'll see why that's going to make my life easier, because remember, I'm looking for where this derivative is equal to 0. So let's see what we have in the numerator. So here we have a 2x. Here we have a 6 times negative 2x, so minus 12x. And then here we have a negative 2x squared times negative 2x, so that's going to be plus 4x cubed. Okay, and that's going to be all over, so the 2's in the denominator, and this whole thing goes in the denominator, just the square root of x squared plus 3 minus x squared squared. All right? Now, the reason why I said this is nice that this is all in the denominator, because this is a fraction, so the only thing that we have to look at for when this expression is equal to 0 is when the numerator is equal to 0. So I just have to solve for x cubed, okay, and 2 minus 12, so minus 10x equal to 0. All right? So let's see what we have here. Let's factor this out. So I can factor out a 2x. So I'm left with 2x squared minus 5 equals 0. So we have either x equals 0, or here 2x squared minus 5 equals 0. So x is going to be equal to, so 5 divided by 2. And now I'm going to take the square root. Now remember, here we have to take the positive and negative square root. And these are all our critical points. All right. Now, because I'm working on this closed interval, I don't have to start, justifying what's a max, what's a min, figuring out if it's an absolute max or min. I just have to test all the important points. All right. So I'm going to use this version of the distance, the simplified version, and let's see what happens. All right. So let's measure the distance at 0. That will be an easy one. So what do we have? This is just 0 squared. Okay, so that disappears. 3 minus 0 is 3. So the square root of 3 squared is just 3. Okay, now that shouldn't be surprising, because when x is equal to 0, my point is at 0, 6. So we kind of already knew that this distance was equal to 3. That kind of tells us, kind of indicates we didn't make a mistake here. All right, at least in coming up with our distance formula. So now let's calculate the endpoints. So my distance at, and this is where I realize all the x's are being squared, so it doesn't matter whether it's negative root 6 or positive root 6. So I'll put here, both of them should give me the exact same result. Okay, so here we have the square root of root 6 squared is just going to be 6 plus, and then here we have 3 minus root 6, so again squared, so this is just going to be 6, so 3 minus 6 is negative 3. Okay, squared. And so that gives us here, what do we have? Square root of 6 plus 9 is 15. Okay, so now here, the square root of 15 is going to be something, well, less than 4, but greater than 3, for sure. Because you got to think, square root of 9 is 3. So this is greater than my distance at 0. All right, so definitely these are not going to give me my absolute mins. All right, so the last one to check are the other critical points here, or critical numbers here. And again, because x is being squared, I get the same answer whether I input positive or negative, root 5 over 2. All right, so let's see what we get here. Square root of, so here, root 5 over 2 squared is just going to be 5 over 2. Okay, and plus, here we have 3 minus, again, root 5 over 2 squared is just going to be 5 over 2. All right, and squared. Okay, and let's do a little bit of, oh, sorry. Make sure you can see that here. So what do we have? We have 5 over 2 plus, so this is 6 over 2 minus 5 over 2. So that's 1/2 squared, so plus a quarter. And that gives us, so this will be 10 over 4 plus 1 over 4 is root 11 over 4. All right, so the question is this less than 3? Well, 11 divided by 4 is less than 3, so this is, that would be about the square root of 3, which is definitely less than 3. Okay, so this is definitely less than 3. All right, so when we look at our critical points and we look at our endpoints, we see that these are the ones that give us the smallest distances. But this means now we do have 2 values, which we said was unsurprising, that if I had one here, I should have another one on the other side. And let's take a look now that we've determined where our optimal values occur. In this case here are minimum distances. Let's go see what question they ask us. And here they say find the point or points on the parabola that are closest. So we have the x values, we just have to find the y values. Okay, now again, when I find y at either one of these values, the x is being squared, so it doesn't matter whether I'm taking the positive or negative square root. So let's calculate it. 6 minus root 5 over 2 squared is just going to be 5 over 2. So this here is equal to, so this is 12 over 2 minus 5 over 2 would be 7 over 2. All right, so that means my final answer, the 2 points that have a shortest distance to 0, 3 are given by, so my x value is going to be negative root 5 over 2 and y value of 7 over 2, or the other option is positive root 5 over 2 with, again, the same y value of 7 over 2. All right, and there's our final answer. So let's just recap, because we did kind of have to do a bit of everything in our algorithm here. So step number 1 was to come up with an equation for what we needed to minimize, which in this case here was the distance. Okay, we had to do a substitution by replacing the y value of that point with the expression given in the equation. We determined that we could work on this domain of values. Then we did our calculus to determine our critical points. And then we use the critical points and the endpoints, because we work on a closed interval, to determine which gave us the smallest distance. And then from there, we went back and we answered the question that was posed. All right, that's it for this one.